Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 5, Applying Newton's Laws, Video 6. Today's topic is dynamics of uniform circular motion. The objectives are understand why a force is needed in uniform circular motion, be able to draw free body diagrams of a given situation, and solve problems involving uniform circular motion. Characteristics of uniform circular motion. In uniform circular motion, the object's velocity has constant magnitude, but changing direction. Therefore, the object is accelerating. The net force providing this acceleration is called centripetal force. Both the acceleration and net force are directed toward the center of the circle. Velocity is tangent to the circle. Here's a diagram showing acceleration and force pointing toward the center of the circle, hence centripetal acceleration and centripetal force. Velocity is tangent to the circle. Here are the equations for uniform circular motion. T is the period, the time for one circle, equals to the distance of one circle, which is circumference, divided by the speed, which is constant. F net is m times a rad. A rad is the same as centripetal acceleration. A rad also equals v squared over r. You can derive this equation. Take a look your textbook. So it shows you how to derive this equation. And if we substitute t equals to 2 pi r over v and v equals to 2 pi r over t, we can get a rad equals to 4 pi squared r divided by t squared. Let's take a look at our first example, force in uniform circular motion. A sled with a mass 25 kilograms rests on a horizontal sheet of essentially frictionless ice. It is attached by a 5-meter rope on a post set in the ice. Once given a push, the sled revolves uniformly in a circle around the post. If the sled makes 5 complete revolutions every minute, find the force exerted on it by the rope. So first, we need to draw a diagram and a force body diagram, free body diagram. So on this free body diagram, there are 3 forces: normal force and weight. By the way, up is positive, down is negative, and x is pointing toward the center of the circle. So N and W cancels. This F is the tension, which is the force providing centripetal force. So Fx equals F equals to m times centripetal acceleration or radial acceleration. There are 2 equations for radial acceleration. Which equation do we use depends on what we know. What is given to us is r is given to us. And the other thing given to us is really the period, because it tells us the sled makes 5 complete revolutions every 60 seconds. That means each revolution is 12 seconds. So we also know t is 12 seconds. So we use a rad equals 4 pi squared times r over t squared. Substitute everything in and you will have this answer. What does this answer, this whole process tells us? So it tells us a greater force would be needed if the sled moves around the circle at higher speed. In fact, if you double the speed, A would increase by 4 times because the relationship between A is direct squared. However, if V is constant, if we increase R, A would be halved, hence the force will be halved. So that makes sense, right? Because if R is doubled, the sled doesn't have to turn that fast. It can turn slower. Therefore, you have less acceleration, less force is needed. The conical pendulum. So an inventor proposes to make a pendulum clock using pendulum bob with mass m at the end of thin wire of length L. Instead of swinging back and forth, the bob makes a horizontal circle with constant v, with the wire making a constant angle beta with the vertical direction. This system is called a conical pendulum because the suspending wire traces out a cone. Find the tension F in the wire and the period T. So to draw a situation diagram, we have this. So basically this is the wire L, and as it turns, you'll have a shape of the cone. Here is the free body diagram. There are 2 forces, tension force and gravity. So tension force has 2 components. One is upward y in the positive y direction. This is the force to overcome gravity. The other force, F times sine theta, sine beta, is the one providing centripetal force. So the two directions, Fx equals F sine beta, this one equals the centripetal force, and the y direction cancel out mg. So from y direction, we can find F. F equals mg divided by cosine beta. How do we find t? To find t, we have to use this equation. A rad equals 4 pi squared r over t squared. In this case, r equals L times the sine beta because it's opposite of the beta. And a, what is a? Well, from this equation, if we know f, we can use the top equation to find a. A equals to g times the sine beta divided by cosine beta. You substitute f in the first equation, then you get rid of this f. So sine beta over cosine beta times g equals to a rad because m cancels out. So now you substitute a rad into the a rad equation, you'll have this expression. You can set it up. T, solve for t equals to 2 pi L times cosine beta over g. So from this results, we can figure for a given L, as beta actually increases, cosine beta decrease. That means t would decrease. As a matter of fact, if the pendulum start like this, it will go much, much faster than this way, okay, small beta. But on the other hand, as beta increases, cosine beta decrease, so f will become very, very big. So beta can never be 90 because if beta is 90, f would be infinity and t would be 0. Another example, running a flat curve. A sports car is running a flat, unbanked curve with radius r. If the coefficient of static friction between tires and road is mu s, by the way, when a car running a curve, the static friction is providing the centripetal force. What is the maximum speed Vmax at which the driver can take the curve without sliding? Here is the situation, the diagram, and here's a free body diagram. Again, you'll have N and mg cancels out each other. So the static friction force is the one providing centripetal force pointing toward the center. So in force in the x direction equals to Fs, this equals to centripetal force. And force in the y direction equals to 0 and equals to mg. Fs equals to mu s times n. This is a maximum static friction. And from here, you can figure out the maximum velocity Vmax. So you can solve for Vmax is square root of mu s times g times r. So from here, you can see Vmax actually does not depend on the mass. It only depends on coefficient of friction and the radius. Obviously, the bigger the radius, the bigger the V you can have because it's directly related to the square root of r. It kind of makes sense. The bigger r you have, that means the faster you can drive, right? Another thing is the more coefficient you have, the rougher the road, the more speed you can also have. So you will have less speed on the rainy or a snowy day than on the regular day. So car speed is slower. If the car speed is slower than this, that means the force required is less than the maximum possible value, and the car can easily make the curve. However, if the car goes faster than the maximum speed, if V is bigger than Vmax, that means R has to be bigger, right? You can still turn, except you will turn off the road because R is too much. And mu s, if mu s is reduced by rain or snow, Vmax has to be reduced also. So you have to be careful to drive in the rain and the snow. Running a banked curve. So for a car traveling a certain speed, it is possible to bank the curve at just the right angle so that no friction at all is needed to maintain the car's turning radius. When a car can safely run a curve, even then the car can safely run a curve even on the wet ice. So your engineering firm plans to rebuild the curve in the past example so that car can move at a speed V, can still safely make a turn even with no friction. So what angle beta should be the curve should the curve be banked. So here's the situation of banked curve. Here's the free body diagram. There are two forces, gravity and normal force. This normal force has two components. The positive y component is to overcome your weight, and the x component, again pointing toward the center, is the one providing centripetal force. So Fx equals n times sine beta equals providing centripetal force mv squared over r, and the y direction that cancels out with mg. So from the second equation, you can solve for n. From there, you can solve for, you substitute n into the first equation, you can solve for v. You can solve for beta. So beta equals inverse tan v squared over gr. So from here, it tells you the banked angle actually does not depend on the mass. It depends on the speed and radius. So in the design of highway, curves are often banked for the average speed of traffic over them. For example, if r equals 230 meters and v equals 25 meters per second, which is about 55 miles per hour, then your beta should be 15 degrees, which is within the range of the banking angle on highways. Steep banked curves are found at car raceways. That's because at car raceways, v is a lot bigger, so beta has to be bigger. Banked curves in the flight of airplanes. So when you fly an airplane, you probably have seen that when the airplane have to turn, you will see the airplane has to tilt. This is because when the airplane has to turn, there has to be a force providing centripetal force. So where is that force coming from? Actually, it's coming from lift force. This lift force has to be at an angle to provide centripetal force. So there are two components of lift force. The vertical one is to overcome gravity, and the horizontal one is the one providing centripetal force. So it's very similar to banked curve. So the vertical one is L cosine beta, because this is the beta. Cosine is adjacent, that equals to mg. Sine one is the one providing centripetal force. So you can solve for tangent beta equals v squared over g times r. Another example, a passenger on a Conical Ferris wheel moves in a vertical circle of radius r with constant speed v. The seat remains upright during the motion. Find expressions for the force the seat exerts on the passenger at the top of the circle and at the bottom. So sketch the two positions. Here's a free body diagram. At the top, you have two forces. At the bottom, you have two forces. Since at the top, the net force is downward, so the normal force has to be less. On the other hand, the bottom, the normal force has to be more than gravity to provide centripetal force pointing toward the center. So after you solve it, you'll have the n at the top and n at the bottom. So as you can see, at the top, the force is less than at the bottom. If v is large enough, so this g minus v squared over r equals 0, the passenger will feel weightless. You will have no normal force. And you will need a seat belt to buckle you in. On contrary, on the bottom, you don't ever have that problem because your normal force is always greater than gravity, so you feel a lot heavier. When you move a ball in a vertical circle, the net force on the ball has a component toward the center of the circle, but also has a component tangent to the circle. So the net acceleration is not purely radial. So that means your speed is not constant. Test your understanding. A satellite are held in orbit by the force of our planet's gravitational attraction. A satellite in small radius orbit moves at higher speed than a satellite in the orbit of a large radius. Based on this information, what can you conclude about Earth's gravitational attraction for the satellite? So we know force is directly proportional to speed squared. So when you have higher speed, you have greater force. When you have lower speed, you have smaller force. That means the force actually decreases with increasing distance from the Earth. The further you go, the less force you'll have, because this force is really gravitational force. Remember, we learned gravitational force is inversely proportional to r squared. So the answer is 3. That's it for today. Thanks for watching. See you next time.